Hello, my name is Dr.Randa. I'm 15 years old. I'm a student at LFP and I'm doing an internship with Dr.Randa Asaad at the American University of Sharjah. Today I'm going to be taking you through chapter 1 of the book she has written titled Stars. We all know what stars are, right? We've all looked up at the sky and seen this beautiful piece of art. We love stargazing. Stars are one of the most beautiful things to look at. But have you ever wondered how they function? What are the physics behind them? All your questions are going to be answered today in chapter 1. So this chapter consists of 9 main parts. 1. An overview of stellar evolution. 2. The HR diagram. 3. Stellar evolution on the HR diagram. 4. The HR diagram and the CMD. 5. Magnitude. 6. Colors. 7. Reddening. 8. It's a long one. Using stellar evolution to obtain ages of star clusters. And finally, 9. Metallicity, or the chemical composition of a star. So before we start with part 1 of this chapter, before we get into any details, we need to define what a star is. We need to have a brief definition of what a star is before we get into any specifications. So, as written in the book, stars can be roughly described as hot balls of gas. They vary in colors, masses, and sizes. They undergo a life cycle driven by the nuclear reactions happening in their core. So we need to take a few important things out of this definition. First of all, we need to know that stars are in a spherical shape. So they are balls. Second of all, we need to know that they're made of mainly gas, very, very hot gas. Third of all, we need to know that they undergo a life cycle. Meaning, just like us humans, we have a date of birth, we go through different phases in our lives, where we start with childhood, and then we become teenagers, and then adulthood, and then eventually we die. Just like us humans, stars undergo a life cycle too, meaning they are born somewhere. They do go through different phases in their life that we're going to go through in part 1 of this chapter, and they do also eventually die off. One last thing to take out of this definition is that they're powered by what is known as nuclear fusion. Nuclear fusion is something very, very important for stars. It's actually what powers them. Just like fuel powers a car, nuclear reactions is what powers a star. You cannot have a star without nuclear fusion, and we're going to get to what nuclear fusion is later on in this chapter. So, now that we've defined the star, we can start with part 1 of this chapter. Overview of stellar evolution. In this part, we're going to get introduced to the life of a star. Where it's born, how it's born, what are the different phases it goes through in its life, and how it dies. We're going to break it down to 9 main phases in a star's life. It all starts here in phase 1, in what is known as an interstellar cloud, also known as a nebula. Here's a picture of it. Yep, they're pretty beautiful. So an interstellar cloud, or a nebula, is a cloud of gas, made of mainly 71% hydrogen and 21% helium. And the rest of the percentage is just some molecules of dust, carbon, silicate, and iron. Before we move on to phase 2, it's important to know that in an interstellar cloud, all the particles are in the molecular form, which is what gives it the name of a molecular cloud also. So all the particles in our interstellar cloud, whether it's gas or dust, are in the molecular form. So what happens now is that due to gravity, our interstellar cloud will divide into what is known as gas clumps. So these, due to the rotation of these gas clumps, they will form disks. So the gas clumps is in the form of a disk. And once this happens, the hydrogen, which is initially in the molecular form, will turn into the atomic form and eventually the ionized form, meaning it's going to have an electrical charge. So our disks, which are known as gas clumps, will have a center. And this center is what is known as a protostar. So a protostar is a very hot and dense core. So these are the first 2 main phases in a star's life. It starts in an interstellar cloud, followed by a protostar, the hot and dense core of what is known as a gas clump. So in this hot and dense core, the protostar will increase in density and in temperature. And then at one point, the temperature in the core of the protostar will reach 5 million Kelvin. Kelvin is a unit of temperature for those of you that don't know, and 0 Kelvin is equivalent to minus 273 degrees Celsius. So 5 million Kelvin is very, very, very hot. What lets us call it a main sequence star is that it has what is known as hydrostatic equilibrium. Big words. So let me explain what hydrostatic equilibrium is. Hydrostatic equilibrium is when the force of nuclear fusion is equivalent to the force of gravity. We all know what gravity is. We know what the force of gravity is. Gravity is something we experience every day. It's the reason why my pencil falls towards the floor when I let go of it. But what is the force of nuclear fusion? What is nuclear fusion? Let me explain that to you. Nuclear fusion is the collision of atoms in the core of a star. So let's take two hydrogen atoms, because this is what the star is fusing when it's a main sequence star. Let's take two atoms of hydrogen and collide them. This collision will release an insane amount of energy. And this process is what is known as nuclear fusion. So we have explosions happening in the core of the star, collisions, big amount of release in energy. But this release in energy, you would think that because it's explosions, you would think the star shouldn't be stable, shouldn't be kept together. But gravity keeps it together. So the force pushing outwards, which is nuclear fusion, is equivalent to the force pushing inwards, which is gravity, and this is what keeps the star stable. Last thing to say in this phase is that a star spends most of its life as a main sequence star. Our sun right now is a main sequence star. A star actually spends 80% of its lifetime as a main sequence star, meaning it's fusing hydrogen in its core. Do you guys remember in the beginning of the video when I said that nuclear fusion for a star is like the fuel for a car? We all know that the fuel of a car runs out. We should also know that nuclear fusion for a star also runs out. This is what happens in the subgiant phase. The hydrogen in the core of the star is exhausted. We can no longer fuse hydrogen in the core because our fuel ran out. What happens here is that the hydrogen will continue to fuse, but in a shell surrounding the core. So our core will no longer be hydrogen, but it will now be helium. But there will no longer be nuclear fusion happening in the core, but it will continue in a shell surrounding the core. So we now have a layer of hydrogen followed by a core of helium. In phase 4, the subgiant phase, we have the helium core surrounded by a hydrogen shell. But it is important to note that nuclear fusion is not yet happening in our helium core. The red giant evolutionary stage is when our outer layer of hydrogen goes down in temperature due to its expansion. So, as the outer shell of hydrogen is expanding, the core is still contracting. And when the core contracts, the temperature increases. So as the temperature increases, we're going to eventually reach a temperature high enough to fuse helium. Just like we reached a temperature of 5 million Kelvin to fuse hydrogen. We will reach a temperature high enough to fuse helium. And the point in time where we reach a temperature high enough to fuse helium, and helium is being fused in the core, this is known as the helium flash. Phase 6 is quite simple. As the title says, it's the helium burning stage. It's the period of time where the star is fusing helium in its core. This stage will last until, just like our hydrogen got exhausted, our helium will get exhausted. And when the helium is exhausted, that's when we pass to the next phase. The helium will keep fusing in the core until it's exhausted. This will leave behind a carbon-oxygen core, and the nuclear reactions will continue in a shell surrounding the core, but this time it's a shell of helium. So we have a layer of hydrogen, followed by a layer of helium, and a carbon-oxygen core. So this phase, where the nuclear reactions again stop in the core, and the surface temperature again decreases because of its expansion, this phase is known as the asymptotic giant branch stage. Okay, we have a carbon-oxygen core. You guys may think now that due to contraction, we're again going to get to a temperature high enough to fuse carbon and then oxygen. But unfortunately, it's not the case. Not for this type of low-mass star at least. This is why this is phase 8A. We're going to have a phase 8B, where the outcome may be different because of the mass of the star. So what's going to happen now is a planetary nebula. This is a peaceful ejection of our layers of hydrogen and helium that are going to be ejected into the space around it, which is known as the interstellar medium, the material filling the space between the stars. So this is our planetary nebula. It's an ejection, and this is the end of our low mass star. This is where it ends. But our carbon-oxygen core will survive, and that is going to be phase 9. So here's our planetary nebula. Our layers of hydrogen and helium will be peacefully ejected, and they're going to be used as material for stars later on. But our carbon-oxygen core will remain, and it is now called a white dwarf. A white dwarf is a very small and very dense core. How dense, you may ask? In a single teaspoon of white dwarf material. If I go to a white dwarf and just take it with a teaspoon, just like that. This teaspoon in the gravity of Earth, on Earth, will weigh 5 tons. That is how dense it is. So, quick recap for a low mass star. It starts in an interstellar cloud, followed by a protostar, and then a main sequence star. 80% of its life is spent as a main sequence star. It's going to fuse hydrogen and then helium, and then eventually get a carbon-oxygen core. Our layers will be peacefully ejected into the interstellar medium, and we're going to have a white dwarf, and this is the ultimate fate. So, a high mass star has the same starting processes as a low mass star. It is going to start as a protostar. It is going to become a main sequence star, but it's a bit bigger than this main sequence star. But the difference is here, in the next phase. The thing is that for a high mass star, it will reach a temperature high enough to fuse carbon, and then a temperature high enough to fuse oxygen, and even a temperature high enough to fuse silicon, and then eventually a temperature high enough to fuse iron. So we're going to have an outermost shell of hydrogen, followed by a layer of helium, and then a layer of carbon, and then a layer of oxygen, and then a layer of silicon, and then finally a very, very hot and very dense core of iron. And this is what makes a high mass star different than a low mass star. Iron production is the last thermonuclear process able to produce energy. Any further process will result in what is known as a supernova. So what's going to happen is that our huge, massive star is going to collapse into itself in a very, very short period of time, in about a quarter of a second. Our huge star is going to collapse into itself and explode, producing an insane amount of energy in what is known as a supernova. Boom! This is our supernova. Yep, I know, it got a bit messy. It's even worse in the real scale. The result of a supernova is either a neutron star or a black hole. If you were shocked by the density of a white dwarf, if you thought 5 tons in a tablespoon is something amazing, you're in for a treat for a neutron star and a black hole. Let me tell you how dense a neutron star is. In a single centimeter cube of a neutron star, a centimeter cube, imagine that. In that centimeter cube, you can fit every single car of the United States of America. That's how dense it is. Now for a black hole, well, it's infinitely dense. You can put anything inside a black hole. You can put everything inside a black hole. It's a point of infinite density. One last thing to mention before we move on to the next part is that at very high temperature, photons, which is the particle of light, possess enough energy to destroy very heavy nuclei. This process is known as photodisintegration. And photodisintegration is so powerful, the photons possess so much energy that in the period of time where the star is doing photodisintegration, it can redo what the star has been doing its whole entire life, which is producing protons. So in a very short period of time, photodisintegration can redo what the star has been doing its whole entire life. By that I mean maybe a billion years. In a short period of time, it releases as much energy as the star has been doing its whole entire life. Now that's a big amount of energy. One last thing, we're going to go through the time scale of each reaction sequence for a star. So let's take a star that's going to live for approximately 8 million years. So this star is going to fuse hydrogen for about 7 million years. It's then going to fuse helium for about 0.5 million years, followed by carbon burning for 600 years, and then neon burning for only 1 year, and then oxygen burning for only 6 months, and then finally silicon burning for 1 day. I said this just to make you guys realize that most of a star's life is spent fusing hydrogen. So, part 2, the Hertzsprung-Russell diagram. So the Hertzsprung-Russell diagram is a graphical tool used by astronomers to classify stars according to their effective temperature, otherwise known as their surface temperature, their luminosity, their absolute magnitude, and their spectral class. So, it is important to note that due to historic reasons, our x-axis actually goes down as it goes to the right instead of up. I don't know, it's weird, but it's just how it is. So, our x-axis goes down as it goes to the right. So, effective temperature is related to spectral class. In other words, a hotter star is going to be blue, and a colder star is going to be red. So the redder the star, the more cold it is. And the bluer the star, the more hot it is. So effective temperature and spectral class are related. The same goes for absolute magnitude and luminosity. The higher the luminosity, the lower the magnitude. We're going to explain why the magnitude is lower when we get to the part of magnitude. But for now, you also have to know that luminosity is related to mass. So stars higher up the diagram have a bigger mass than stars lower down the diagram. Here you can see the white dwarfs, our main sequence, which is where most stars are observed because they spend 80% of their lives in this stage, so it's easier to observe them while they're as a main sequence star. We have the giants and the red supergiants, and this is our HR diagram. Okay, we got an overview of stellar evolution, and we got introduced to the HR diagram. But now for part 3, we're going to see stellar evolution on the HR diagram. How the position of the star on the HR diagram changes as time goes by. So we're going to talk about 4 main points: the turn-off point, the horizontal branch, the asymptotic giant branch, and then finally the blue loop. So stellar evolution right here is represented by the letters A, B, C, D, E, F, G. Let me draw that for you real quick. So it starts here in interstellar cloud. The position will move up to B, go through the turn-off point, the horizontal branch. It'll go up, this is the asymptotic giant branch, and then finally the blue loop. This is stellar evolution on the HR diagram. But let me now explain each of these points. So the star will be positioned on the main sequence depending on its initial mass. If you guys remember, I said earlier, luminosity is related to mass. So the higher the luminosity, the higher the mass. And this is how the stars will be positioned on the main sequence. So let's start with our first point, the turn-off point. As you can see here, the turn-off point is at the edge of the main sequence. It's when the star is leaving the main sequence. If you guys remember our overview of stellar evolution, this is the helium flash. This is once the star stops fusing hydrogen into helium, but starts fusing helium. This is the turn-off point. And let me just say one thing. This path is for a random star. It is not the same path for every star, because we could have the turn-off point up here for a high mass star, the turn-off point down here for a very low mass star. This is just the path of a random star. So we said the turn-off point is the equivalent of the helium flash. Now for the horizontal branch. The mass of the star will determine how the star will leave the red giant branch, which is the RGB, after the healing flash. So our low mass stars are going to drop in luminosity and increase in effective temperature, in surface temperature otherwise. So our drop in luminosity is not very significant. I didn't draw it properly here, but I will show you a proper HR diagram in a few minutes after I finish explaining this. So we are going to have a drop in luminosity, so our horizontal branch should have a small declination. But we're going to have a big increase in surface temperature, and this is what is going to form our horizontal branch. Again, decrease in luminosity, so here our horizontal branch should go down a bit, but increase in temperature. This is the horizontal branch. So when the helium gets exhausted in the core, our luminosity will again increase and the temperature will decrease. But this time the luminosity will go up almost vertically. This is actually the most luminous phase in the life of a star. As we can see here, the luminosity goes up by a big amount between the points D and E. And the effective temperature will decrease. And finally, the blue loop is quite clear on our diagram here. The effective temperature will keep on going up, and then what's gonna happen is a planetary nebula. We mentioned that in the overview of stellar evolution. So this is the path that the star is going to follow as it goes towards its death. Right here is our blue loop between the points E and G, and it's going to end at the bottom left of the diagram where the white dwarfs are. Part 4 is a rather short part. We're going to be looking at the HR diagram and the CMT, the Hertzsprung-Russell diagram, and the color magnitude diagram. So we're going to see that the HR diagram is actually a theoretical diagram, and the CMD is the corresponding observational diagram. So we know that the HR diagram is a diagram of luminosity versus surface temperature. So the corresponding diagram is the CMD, which is color and magnitude. So we need to know that magnitude is related to luminosity and color is related to surface temperature. So we said this is luminosity versus surface temperature, color is related to luminosity, and magnitude is related to surface temperature. Why is this theoretical and this observational? For the simple fact that luminosity and surface temperature are not observable quantities from Earth. These are theoretical, they're calculated. But color and magnitude are observable quantities from Earth, therefore this is an observable diagram, while this one is a theoretical. Now moving on to part 5 in our chapter, magnitude. So the magnitude of a star is its brightness, but in astronomy we don't use the word brightness. You can use the brightness to describe the brightness of your phone, but for stars, we use magnitude. So we're going to talk about two different types of magnitude. Apparent magnitude and absolute magnitude. It is important to note that before we get into these two types of magnitude, we need to know that the lower the magnitude, the brighter the star. So a star of magnitude, let's say 1, is brighter than a star of magnitude 6. Our Sun has a value of apparent magnitude of minus 27.3. That's very bright. But a value of absolute magnitude of only 4.8. Let me explain that. So this value for brightness is the value of the star, of the brightness of the star at the distance it is from Earth. But this value is the value of the star as it is at a distance of 10 parsecs. So how bright would our sun be if we put it 10 parsecs away? It is currently 1 astronomical unit away, which is 150 million kilometers. And its brightness is minus 27.3. But what would be its brightness if we put it at a distance of 10 parsecs, which is equivalent to 3.262 LY, light years. This is the difference between apparent magnitude and absolute magnitude. On our HR diagram, we use absolute magnitude because we put all stars at the same distance from Earth and then measure their brightness. Now for part 6, colors. So our astronomical images are taken through different filters that have different sensitivities to different wavelengths. Meaning that a red star is going to be brighter through a red filter than it is going to be through a blue filter. We're going to talk about a system, the most famous system actually used in the optical range, which is the Johnson-Cousins system. This system uses UBVRI, U for ultraviolet, B for blue, V for visible, R for red, and I for infrared. So to obtain the color of a star, we just simply need to compare any two filters. So mainly we use B minus V, this is the most used, but it works for all other filters too. It works for, I don't know, R minus V, V minus I, B minus R, I minus R. I could have written all the possible comparisons, but it would have taken me a very long while. We're going to end this part of the chapter by stating Wien's law, which says that the wavelength of maximum emission, lambda max, is proportional to the temperature of the star encountered. Now we're going to talk about a concept called reddening. So if the light emitted by a star passes through interstellar dust, the dust filling the space between stars, it will get scattered. And that scattering is not uniform for all wavelengths. In fact, shorter wavelengths tend to get scattered more than longer ones. So bluer light will get scattered more than red ones. Therefore, when we observe stars, we're going to observe them redder than they actually are. This is known as color excess. And we can get this by a simple equation. Color excess, so the excess of B minus V, is equal to B minus V observed minus B minus V emitted. Using stellar evolution to obtain ages of star clusters. So the ages of star clusters can be given to us using stellar evolution on the HR diagram. So we notice that the turn-off point can give us information about the ages of star clusters. So the lower the turn-off point, the older the cluster. So let me just remind you that the turn-off point is the moment the star stops fusing hydrogen into helium and starts fusing helium. This turn-off point is on the main sequence. So the lower the turn-off point, in other words, the more it's to the right, the older the star clusters. So for star clusters that are roughly 1 million years old, the stars will mainly be on the diagonal, being the main sequence. For clusters about 100 million years old, we notice that the blue points are moved towards the right, so the turn-off point is lower. And the same goes for star clusters that are about 10 billion years old. Our chapter is coming to an end. This is the final part, metallicity. In other words, here we're trying to find the chemical composition of a star. So the chemical composition of a star is represented by 3 letters: X, Y, and Z. X representing the fractional percentage of hydrogen in the star, Y representing the fractional percentage of helium in the star, and finally Z representing the fractional percentage of all the other elements in the star other than hydrogen and helium that have an atomic mass larger than 4. So X plus Y plus Z is always equal to 1 because obviously all the elements combined together are going to give us a result of 1. And we're going to take the example of the sun. Our sun has a fractional percentage of hydrogen of 0.71 and a fractional percentage of helium of 0.27, and finally all the other elements are 0.02. So if we add up these 3 values, 0.71 plus 0.27 plus 0.02, we're going to get a result of 1. Thank you guys so much for watching, and again, thank you Dr.Randa Asaad for giving me this wonderful opportunity. I'll see you guys in chapter 2.